Today's webinar will be about thermal interface materials and also about the measuring instrument for these materials, the so-called TIM tester. So before we go on, maybe I introduce myself. My name is Erika Hahn. I studied physics at the University in Erlangen, and I'm working for LINSEIS since 2020. And I'm responsible here for the application measurements in the lab for the field of thermal conductivity and also thermal electricity. And for those who do not know LINSEIS, LINSEIS Mesquerete is founded in 1956 in Selb by Dr. Maximilian LINSEIS. Here you can see him. LINSEIS started firstly with such data loggers, and nowadays we are producing instruments for the thermal analysis and also for the thermal conductivity characterization, as well as thermal electricity. The company is now led by the son of Maximilian LINSEIS. This is Klaus LINSEIS, and also by his sons, Florian LINSEIS and Vincent LINSEIS. So we manufacture our instruments here in Selb in Germany, in Bavaria, have an own sales and service locations in the US, China, India, and more than 65 distributors worldwide. So as already mentioned, we are producing measuring instruments for the thermal analysis, thermal conductivity, and thermal electrics, but we also offer some service measurements in our lab, like it is shown here in this picture. So our product range you can see here on this slide. So we have DSCs, thermal gravimeters, the combination of these, the STAs. We have dilatometers. We can do thermomechanical analysis and the thermal conductivity measurements, thermoelectric materials, and we can also analyze the thermal conductivity and the thermoelectric properties of thin films, as well as the Hall effect. And what makes us unique is that we, so to say, do not have a standard instrument, but we try to optimize the instrument for each customer. So we produce customized instruments. So as already mentioned, the TIM tester belongs to the thermal conductivity instruments. Generally to this field belong the laser flash analyzer shown here, the TIM tester, the THB, and the HFM, which is mostly suited for building materials or insulation materials. So today's webinar will be mostly about the TIM tester and also thermal interface materials. What are these in general? And on this picture, you can see is, so to say, an older version of the TIM tester. We modified the system and now it looks like this one here in this picture. So in general, the TIM tester is a universal device for the determination of the thermal conductivity, and the system is optimized for thermal interface materials and is measuring the thermal conductivity according to an ASTM norm, to which we come later. So here you can see the agenda of today's webinar. First, we have a look onto thermal interface materials in general. Then we will have a look onto the ASTM norm, which I just mentioned. And then we will have a look how this ASTM norm is realized with our TIM tester. And I will show you some application examples of the TIM tester. And in the end, the TEG tester for thermal electric generators, which is a modification of the TIM tester, will briefly be shown. So coming now to thermal interface materials in general. So modern technology and technical devices became much smaller and at the same time also more powerful. And the packaging of these integrated circuits is increasing. And thus, the thermal management, how to solve the heat dissipation, becomes a crucial parameter, since overheating of some components can also lead to failure. And the heat sinks are not as efficient as they should be, so often they cannot dissipate the heat optimally. And this depends on the contact surface of the material. And despite modern manufacturing processes, a certain surface roughness remains on these components, as shown here. And there are some microscopic air inclusions, which, so to say, do not dissipate the heat properly. And here come now the thermal interface material. And the thermal interface material should fill these voids, and by that it establishes a larger contact area and enables a maximum thermal conduction with a low thermal contact resistance. So thus, the aim is to improve the thermal contact between the heat source and the cooler in order to get rid of the waste heat. So the pressure and temperature dependent thermal impedance are of interest, as well as the stability of these materials during thermal or mechanical cycles. Thermal interface materials are generally used in many different application fields, like, for example, signal processing, automotive, aerospace, semiconductor industry, telecommunication, or also medical device technology. The classic example would be the cooler, which is connected to a CPU unit of a PC. Here you can see such an example. And there is a typical stack of a mounted CPU with a bracket and a heatsink. And between these components, there are thermal interface materials. So two of them, these are marked. And the thermal interface materials optimize then the heat flow from the CPU through the stack to the environment. And here you can see also some further examples of thermal interface materials. So these are used in a lot of different electronic devices, also in mobile phones, computers, and so on. So the thermal management of these components is very crucial, so that thermal interface materials and their properties are really important. The thermal interface materials can be grouped into three categories according to the ASTM norm. So type 1 would be viscous liquids like pastas, greases, phase change materials, or liquids. So these materials exhibit no evidence of elastic behavior or the tendency to return to the initial shape after deflection stresses are removed. So this is what characterizes this type. Viscoelastic solids exhibit linear elastic properties with significant deflection relative to the material thickness, and examples for that are pads, tapes, foams, or gap fillers. And the third type of the thermal interface materials are the solids, like, for example, polymers, metals, or ceramics. And these type of materials exhibit negligible deflection, like the just mentioned examples. So if some stress is applied to the material, no deformation or just a really minimal neglectable deformation can be observed. To unify the measurement method and some technical specifications, there's the ASTM norm, and this norm, so to say, describes a test method for the thermal transmission properties of thermally conductive electrical insulation materials. And in the following, we will have a look onto the ASTM norm. This ASTM norm describes also how such an measuring instrument should look like, or how it is constructed. And generally, there are two possibilities of measuring the heat flow through the specimen. And one of them is via 2-meter bars with a heater, with a heated and a cooled meter bar. So if this principle is used, a guard heater and a thermal insulation is not required, and the heat flow through the specimen is computed as the average heat flow through both meter bars. So this is also the setup we use with our TIM tester. So we have a hot and a cold meter bar between which the specimen will be placed. The astm norm also defines that the two surfaces of those meter bars have to be parallel within 5 microns and smooth within 0.4 microns. The temperature stability has to be within 0.2 Kelvin. And generally for the measurement, using such a hot plate technique, a sample is sandwiched between those 2 meter bars, and the temperature of these 2 meter bars can also be temperature controlled, so that in this case the heat flow occurs from the upper to the lower meter bar. The temperature in the meter bars is then measured by some thermocouples mounted in known distance. So here are 4 thermocouples placed which measure the temperature, and those thermocouples have a known distance to each other, and by that one can determine the heat flux. The thermal impedance is then calculated according to this formula, where the contact area is divided by the average heat flow through the stack and multiplied with the temperature difference between the hot and the cold surface, so the hot and the cold meter bar. And as mentioned, one determines the thermal impedance with the heat flux, and this is repeated for several sample thicknesses. One needs to measure at least 3 different sample thicknesses because one has to plot it like that. So the thermal impedance is plotted independent of the sample thickness, and this is a linear correlation. So the more different thicknesses are measured, the more accurate will be this linear fit. From the linear fit, one can then determine on the one hand the thermal conductivity. The thermal conductivity corresponds to the inverse of the slope of this linear fit here. And with the y-axis interception here, or the offset, one can determine the contact resistance. In this example, you can see the measurement of a thermoconductive bed. The sample temperature was 50 centidegrees. The hot plate had a temperature of 70 centidegrees and the cold one 30 centidegrees. And one obtained a thermoconductivity of roughly 3.5 watt per meter Kelvin. And if this measurement is performed under elevated temperatures, the thermal conductivity changes typically, and thus the slope of this linear curve will change as well. And furthermore, if the pressure on the sample will be increased, the offset typically here gets smaller because of a better contact from the sample to the meter bars. Then here this offset will be lower. So, and these were the main points of this ASTM norm. And here in the slide, you can see the LINSEIS TIM tester with our realization of this ASTM norm. And we have designed a fully integrated setup. And the system consists of the 2 meter bars, which are here. And these are used to measure the occurring heat flux through the sample. We have two cartridge heaters on the top and the bottom of the meter bars. And these allow us to exactly control the temperature of the hot and the cold side. We have an electromechanical actuator here on the top. This one can be software control and allows us to apply a variable contact force of up to 2.5 kilonewton. This translates into a surface area depending pressure of up to 8 megapascal. In the setup, there is also a load cell for a continuous contact pressure measurement, LVDT, which is used for high precision thickness determination. And these are the main things, so to say, in the TIM tester. And because of this setup, it is possible to run fully automated measurement cycles, including thermal and mechanical aging studies, compression studies, or the influence of temperature and pressure on the thermal transport properties of the investigated samples. Now we come to the TIM tester specifications a bit more in detail. So the system can be in a standard configuration used for measurement in the temperature range from room temperature up to 150 centigrade. With a different intercooler option, one can extend this range from minus 30 centigrade Celsius to 100. Or with another modification, one can measure from room temperature up to 300 centigrade. The meter bars are either round or square, with the size ranging between 25 and 40 millimeters. They are isolated shielded meter bars, and these can be changed. The contact force, as mentioned, goes up to 2.5 kilonewton, which translates then into a contact-dependent pressure of up to 8 megapascal, and the contact force accuracy is 1%. With the LVDT, one can measure the sample thickness. The accuracy here is about 0.25%. And typically, one can measure samples in the thickness range of up to 10 millimeters. And the most investigated sample thicknesses are in the range of 0.1 to 5 millimeters. So the standard meter bars which are used are out of aluminium, and with that one can, for example, measure a thermal conductivity range of 0.1 to 50 watt per meter Kelvin. So another fact here which I should mention is that the limit of 10 millimeter is set since for thicker samples, the heat losses, the radial heat losses, will get a crucial problem. So that this sample setup does not make any sense. So this is why it is recommended to rather measure thinner samples so that the heat losses on the side are not that large. So as already mentioned in the beginning, we build mostly customized instruments. And for the TIM tester, one can, for example, make the following modifications. One can change the meter bars, so the geometry can be changed from round, square, or some individual dimensions. Typically, these meter bars have a size between 25 and 40 millimeters. And what is important here is that the size and the shape of the meter bars affects the maximum possible contact pressure and also the maximum possible gradient over the sample. So this is because the electromechanical actuator is always limited to this 2.5 kilonewton, and depending on the area here, this translates into different contact pressures. The meter bars are available in different materials: aluminum, aluminium, copper, brass, or for example, Inconel. And the different materials are optimized, so to say, for different thermal conductivity ranges, and the standard, which is mostly used for thermal interface material characterization, is the aluminum meter bar. There are also different coatings available for this meter bars: nickel, chromium, zirconium, and one can have a defined roughness. Further modification, which is possible, is extended clamping force range from 0 to 500 Newton. And this setup is shown here on the right. So here there's an extended clamping force range. So one can see here clearly that the top gets longer due to this modification. Using the TIM tester software, one can realize different measurement configurations, and in general, the software is divided into a setting area. One can see the current values of the measurement, and the third tab will be the results, and there are further add-ons which can be realized for different applications in the software. So the settings section is divided into some general information like sample name, manufacturer, and so on. One can add in a large field additional information. And one has here the measurement settings. To this I will come in a minute. One needs to define where the data should be stored and also in which form. For example, here in a PDF in an Excel file. And on the bottom, one can set a temperature profile and can also define the temperature gradient over the sample. So the measurement settings, which are done in the software, differ for each sample type. So for type 1, the viscous liquids, one needs to define the thickness. As mentioned before, one needs to define at least 3 different thicknesses to obtain a good linear fit in the diagram of the thermal impedance independence of the sample thickness. So for type 2, for the viscoelastic solids, one typically defines a compression, which refers to initial thickness. Like in this example, one had samples with thickness 1, 2, and 3 millimeter and defined each a compression of 5 and 20%. For the solids, one defines different thicknesses and can also define different contact pressures. So in the current values window, one will see a graph which shows the temperature of the upper meter bar and the lower meter bar and the average of them, which corresponds to the sample temperature. One can observe the change of the thermal impedance with time. And on the right, one can see the current values for the pressure, the thermal impedance, the measured or defined sample thickness, and can see again here the temperatures. In the last tab, one can see the results. This window will be updated after each single measurement at one sample thickness is finished. And first of all, one can see again the general information about this measurement, and then one can see all the single results and then the end result, which is determined from this graph here. So in this example, a solid was measured where 3 different thicknesses were defined with a contact pressure of each 1 megapascal. So one can see here again the sample temperature, the temperature gradient over the sample, the measured sample thickness, the measured thermal impedance, the measured pressure, and the effective thermal conductivity is also shown. The effective thermal conductivity is calculated for each single measurement using the sample thickness and the thermal impedance. And in the report, one can also see the set values of the thickness and the pressure, where one can check if everything worked correctly. So in this case, it was very good, since the given thickness corresponds exactly to the measured thickness as well as the contact pressure. So, and in this report, one can also see then here this is the graphic representation of the thermal impedance independence on the sample thickness. And in the ideal case, it is a linear correlation. And if some of these points do not fit to this line, something might went wrong. So in the end, then the end results are shown. So the average sample temperature, the thermal conductivity determined as the inverse of the slope from this line, and the contact resistance, which corresponds to the offset in this graph. So this was the realization of the in the ASTM norm defined thermal interface materials tester. And now we come to some application examples. On this slide, you can see a measurement of a paste, which belongs to the type 1. This paste is a glass adhesive, and this glass adhesive is used for structural bonding and especially for the glass sealing of cars, for example. And the adhesive provides a wide range of mechanical properties, so it can be also used to seal and fill gaps in vehicle battery packs or for quarter lights, modular roof assemblies, sunroof systems, or door glasses. And due to the advantageous properties, the advantageous properties are, for example, a high thermal conductivity, a low thermal resistance, vibration damping, and it is compatible with all production processes of a car, for example. And this investigation was done to check the properties of this paste. The paste was directly applied onto the meter bar, and during the decreasing sample thickness, the excess material was squeezed out, and in this case, not removed, but it is also possible to remove the excess material. The measurement was performed at room temperature with a temperature gradient of about 4 to 5 centigrade Celsius. So this means that the upper meter bar was about 2.5 Kelvin hotter compared to the sample temperature, and this also counts for the lower meter bar. The thickness was reduced from 2 to 1 millimeter, and here you can see the measured thermal impedances and the effective thermal conductivity. And in the graph here, you can see that all those points fit very good to this linear fit. And the end thermal conductivity, which was determined, was about 2.6 watt per meter Kelvin. In this example, you can see a PET, which belongs then to the type 2 thermal interface material. Here, the sample temperature was set to 50 centigrade Celsius, and for each sample thickness, a compression of 5 and 10% were defined. So the sample thicknesses were 2.5, about 4, and roughly 6 millimeters. And in these images, you can see clearly here the meter bar form, which squeezed into the material. So the end result here shows that with a higher compression, also thermal conductivity gets higher. And to illustrate that, one has here this diagram where the thermal impedance is shown in dependence on the compression. And also here, the dependence on the sample thickness. The last example belongs to the type 3 materials. This was a gas diffusion layer, and the gas diffusion layer in general plays a critical role in a fuel cell, and there they act as an electrode that facilitates the diffusion of reactants across the layered membrane. And additionally, they control the fuel cell moisture by removing the water outside of the catalyst layer and simultaneously keeping some water on the surface for the conductivity through the membrane. Furthermore, they also transfer heat. And in general, the gas diffusion layers are carbon cloths with either weaved carbon fibers, or they are produced in a form of a carbon paper, which are made out of pressed carbon fibers. In the images, you can see such gas diffusion layers, and these were measured on the one hand in dependence on the temperature, and on the other hand in dependence of the contact pressure. So the sample temperature was increased from 20 centigrade Celsius to 75, and the contact pressure was set to 0.05, 0.25, and 0.5 megapascal. For each sample temperature and for each contact pressure, 3 different thicknesses were measured. And here are the end results, where one can see that with increasing temperature, the thermal conductivity is also slightly increasing. And one can see as well that with increasing contact pressure, the thermal conductivity also increases. Another thing which can be seen here also very clearly is that the contact resistance, so the offset in the graphs, decrease also with increasing contact pressure. So from here, from 8 to about 4, decreasing further to about 2.6. And in the report, there will be also some graphic illustrations like here, where one can again see the dependency of the thermal conductivity on the temperature. So here one can see the results also very clearly. And as mentioned in the beginning, I will want to give an outlook for a modification or another form of the TIM tester, which can be used to characterize thermoelectric generators, which is shown here like it looks like. So with the TEG tester, one can measure the temperature-dependent conversion efficiency of such a generator. And with the TIM tester, it's really easy and fast, since one can connect it really quickly and mount it also very easily. And the advantage is that one can define the clamping pressure to realize or to show also the realistic conditions of such a TEG tester. On the right side, you can see an example of the electrical characterization, and in this case, it was a bismuth telluride thermoelectric module, and here IV scan was performed. One started with open circuit voltage, and change the parameters until one achieved a short circuit current. And these curves here show the power, and these curves are plotted for a maximum power point tracking. So this was just briefly an outlook for the TEG tester, for which application the TIM tester can be also used with a slight modification. So now I'm finished with the webinar, so to say. I want to thank you very much for your attention, and I'm happy now to answer your questions.